Hello, welcome to our SGP Annual Research Updates 2021. My name is Fang Gang. In this video, I will show you a fully anonymous traffic identification method with seismic data. As science developed, roads became more crowded and cars grew in number. For a megacity like Singapore, monitoring human movement in public spaces and understanding the real-time change of the traffic in different sectors is vital for daily traffic management. Traffic cameras are widely used for traffic surveillance and management. With the popularity of smartphones in recent years, mobile data is increasingly used to understand where, when, and how people are moving in the city. For example, during the COVID-19 crisis, Apple and Google released anonymous averaged statistical data based on their location services. However, the use of these methods exposed their shortcomings. Using camera raises severe privacy concerns. Its installation is not flexible enough, and the weather and light limited the function of the cameras. For the smartphone mobility data, it is averaged, therefore has low spatial resolution. Moreover, the data are segmented by different platforms, which requires the concatenation of the heterogeneous datasets before use. In this video, we propose a fully anonymous and high-resolution traffic identification method with seismic technology. On the campus of National University of Singapore, we planted 3 component geophones beside a campus road. When a car drives past the roadside geophone, its induced ground vibrations propagate as seismic wave field and recorded by the geophone. At the same time, we use smartphones to take a video as cross-validation of the post-analysis. Here is a traffic video captured on a smartphone and the corresponding vertical component geophone recordings. From the smartphone video, we can identify 4 vehicles past the geophone. Each red dot represents one traffic event. From traffic recordings, we can find the moving cars generate large seismic amplitudes than ambient noise. However, the amplitude alone is not robust enough to identify traffic events. Take the second traffic event as an example. It is difficult to distinguish it from the background noise only by amplitude. Next, I will introduce a more robust identification method based on seismic spectrogram. For this seismic recording, we apply short-time fast Fourier transform and get its spectrogram. On the spectrogram, road traffic shows strong energy across a wide frequency band. The traffic events show better resolution at high frequencies, like above 30 Hz. This is mainly due to the highly dissipative nature of the near surface. The energy of seismic wave produced by vehicles decay increasingly with higher frequency and longer propagation lengths. Compared with the low frequency, the high frequency is more correlated to moving vehicles close to the sensor. Based on the observation, we summed PSD between 30 Hz and 150 Hz, obtained the red dot line to identify the peaks of energy arrival. 2 parameters, the relative height of the peak, called provenance, and the time interval between the 2 nearest peaks, called isolation, are chosen for each site to account for the site difference. The detected peak of the red dot line corresponds to each individual vehicle. Applying the identification workflow to a 15-minute seismic recording, we identified 18 vehicles. We take the video data as benchmark and further analyze the accuracy of our method. As a comparison, we apply STA over LT method to the same data for vehicle identification. This table shows the statistic of these two methods. From the video, we manually identified 83 vehicles driving on the road. There are 76 vehicles went straight, and 7 made a U-turn. The vehicles went straight, including bus, cars, trucks, motorbikes, and bicycles. For the identification of bus, its 10 meters long wheelbase caused the front and rear wheels to generate two distinct peaks of seismic energy as they pass through the geoform. This increased the probability of false positives for the identification method compared with ST over LT method. Both recall and precision of the spectral method achieve higher score for trucks and cars. However, neither method identifies the bicycle, perhaps because the ground motion caused by the bicycle was too weak to be observed. It should be pointed out that there was a car that went straight past the geophone and smartphone, but was not captured by the camera because of the video shooting angle. Both seismic methods identified this car, which reveals one of the advantages of using seismometer for vehicle identification and monitoring. Overall, both methods achieve high accurate vehicle identification. The spectrogram method is better. Laying out more geophone along the road, we will have a geophone array, displaying the recordings of the array according to the distance. We have a seismic profile. Its horizontal axis represents time, and the vertical represents distance. From this seismic profile, we can not only identify the vehicles, but also calculate their speed. As conclusions, we propose a vehicle detection method based on seismic spectrogram. We demonstrate its feasibility and high identification accuracy. For more applications of seismic data on traffic monitoring, please watch Elite, Alex, and Yumi's videos in this series. Okay, that's all for this video. More information about our research can be found from our website, YouTube, and Bilibili channel. If you like this video, don't forget to like, comment, share, and subscribe.